functions. Already gave some formulation. Again, let's see. So we have three cases. Now in this order, the first one, the Rosenthal representations, that have the Asplund, and the reflexive representations, but in fact, we already proved the third case. It was some kind of prototype to understand what we can do generalizing third case, and reflexive case is for us something we can consider as prototype for first and second cases. Okay, let me recall that in the first case we have f, which is doubly unique property, or it is equivalent. It's a pointwise closure. Consists of continuous functions. So we have here some kind of hierarchy, because first of all we understand it by Banach space theory, because every reflexive is Asplund, every Asplund is Rosenthal. But if we look at our families, it's also understood that each time we have a weaker and weaker condition, it is not so easy to, by the way, to understand why without limit property, the fragmented family, it might be the proof is not so long, but also not so trivial. But we see it immediately from our formulation. Okay, about first and second cases. Let's see, first of all, one direction. So we have two directions. We can say anytime, if and only if and only if. So the one direction, if we already have representation.
I'm sorry to interrupt you, but I know this F for me is still something new. I kind of got used to S and X. So why bother about some F? What is the motivation for this? Why do you consider these functions?
F?
Yes, these families of functions.
So our leading exam is some orbit of some individual function on our dynamical system. And whenever our function is good, in some case, if you consider instead of f, big F, this one, it just will give us the formulations of definitions I already gave. I mean, the definition of Megrelishvili periodic function, of Asplund functions, and the tail function. So it's a particular case. But on the other hand, as I already mentioned, this case is a key idea because we, as we know, the cyclic G-spaces are the building blocks of our G-spaces, of our dynamical systems. That is why many questions can be reduced to this particular case. That is why in most corollaries we use this particular case.
It's a different problem than problem of representing dynamical system.
Right, but so it is not a big secret that in order to understand dynamical system, even any other structure in mathematics, you consider some function. You should understand dynamical system, what you can do. So, what's your tools? Take some function, and this just very interesting moment here. Just maybe your question gives me a possibility, opportunity to to give another side of this theorem. When you have some dynamical system, one of the possible tools is take some function. Now, what we have some translations, right, in dynamical system. So translate consider induced translations of your function. You get this one, just this one. Now, from this class of functions, try to understand how small it is, how good it is, and if you can find sufficiently many good functions, that's a general strategy. So, what's the sufficiently many? Which separates points on our dynamical systems. And what is small? I already mentioned there are several meanings. What is small might be an almost periodic function, equivalence periodic function. We have hierarchy, I already mentioned. So, and Asplund, tame, and so on. So that's a general strategy, and the maximal case is just we consider right uniformly continuous function.
So when you, for example, want to show that something is reflexively representable, then you care about this Fs is a weak compact, right? And then you use David Johnson construction and get a reflexive space. If you want to create Asplund space, you have to show that this orbit is Fs and the pointwise closure is Asplund set. And then if you do the procedure, you get Asplund space.
In the first case, I can agree it's possible, and in one of the versions in my proofs, I used even this one of closure, pointwise closure. You can use it's a kind of dynamical model. What you want. But I am not sure about other cases. It is too complicated. It is somehow related, but we work some dual object, not this object, and this object will be some family of functions which control our situation. So again, what we have here, we have also in our theory. We have some theory because f is a part of, after all, it's a part of some functions. It's a bounded part of C of x. And we need to understand what, how small f is and what is small. Why I put here small families of functions. Because small means that according to possibility to represent it in some good Banach spaces, we have corresponding hierarchy. Also, we have a right uniformly continuous functions, larger class. In the case that our dynamical system is continuous. We have Rosenthal spaces, right, and corresponding classes, tame functions, Asplund, big periodic, always periodic. But in our tame, this corresponds to Banach spaces, to Rosenthal spaces, Asplund. Here reflexive. This is the idea of. Yes.
So when you create this Banach space, do you create it always in the same way that you use the set F to then you take absolute convex hull and then you take those norms and create
right,
space?
Right. That was one of the next my points to explain.
So always you have to find a condition on F to create the correspond to have the
right. So if you already asked it, I can show you something in section H3. theorem, the reflexive case, right? So at some point we need to show that is indeed reflexive or Asplund or Rosenthal, yeah. So it's a very good question because I wanted to speak about this here. For example, when we need reflexivity, what we need, yeah. After all, one of the key results is the Megrelishvili theorem, for example, because if you start from F, which is weakly compact, and then go to the convex pole of symmetric union, so we get again a relatively weakly compact subset. So it's a very important and crucial step in this case.
Yes.
So your question is very sharp, very in order here. But what happens in other cases? And this center of difficulty, I mean difficulty in the proof, during the proof, and also in explanation. Because it requires a lot of other technique and other definitions. I already have it here, maybe I can give some hints about, for example, for a Rosenthal case, okay, what we explore. We explore, maybe it's time to go back. Okay, so we are here. And when we are speaking about, for example, we are speaking about that not matters. Just follow my text because it was in my plan to explain, to answer your question. So let's continue just. So what happens? So for reflexive spaces, I already gave the answers that just use as one of the main steps, Megrelishvili theorem. Okay. So what happens in other cases? What kind of difficulties from Banach space point of view we have? So let's see for these purposes why eventually fragmented captures very essential properties which lead us to corresponding classes. I mean, that's the question. So let's go to this theorem, for example. Here I put a list of some main characterizations of Asplund Banach spaces. So experts in Banach space theory knows that there are many investigations and many words around Asplund spaces, and but much more characterizations. But my choice is not just for our needs and for exactly we need in our proof and maybe justify something. So, where is Asplund space if and only if the dual has Radon-Nikodỳm property? But maybe, by the way, this justifies the name Rn, Radon-Nikodỳm compact spaces. This justification, which its name comes from yoga. Third, every bounded subset is weak star fragmented, very well known, one of the classical results, which is very topological, but captures the Asplundus. But we can reformulate it also in this way, form. Maybe the fragmented family of real bounded domains or the compacta. This is just reformulation of tree. If you go, in order to explain, for example, equicontinuity from continuity, you need to use supremum of your family. This is just the same idea. In order to work with equifragmentability, again, you need supremum. But what is supremum for us? Supremum just a definition of corresponding norms by functions. So the technique behind this guy is quite straightforward, but up to our definitions, what we need, what our okay. If we are here, what just a few few words about Asplund spaces. Any space of this kind is C0 spaces are Asplund, it's well known. And we already several times in our exchanging questions and discussions with Piotr mentioned that CK for the compact space is Asplund if and only if our K is scattering. For example, this explains immediately why C0 or the regular C0 is, or C is Asplund. Also, by Navier-Stokes joint continuity theorem, it is easy to prove that every weakly compact subset is weak norm fragmented. It's a very quick way to prove that every reflexive space is Asplund. Because take some, some bounded subset into the dual, the reflexive space, the dual also reflexive and weak star, everything, it's coincidence of weak star by reflexivity. So again, we see that we have Asplundness, so reflexive spaces, which is why we have it here, reflexive is Asplund. Okay, now go back. So, answering to your question again, one of the main ideas in the proof of Asplund's case, just fourth condition. So, if you have in Asplund's case, we can explain it also here parallelly. So, in reflexive case, the name of the trick is a double limit property. Okay, that's how we can use this way. Of course, is a weak compactness of our, or weak compactness of our bounded subset. It is okay. For Asplund case, what is the key idea? The fragmented families. And why it was natural to think about this? Because we can formulate Asplundness this way, that if you consider the canonical theorem between B and B star, then B in the role of our F is a fragmented family. By the arguments I already gave. So B as F is fragmented. If you think our B as a family of functions on B star is fragmented for B star. The central idea, and what happens in order to manage Megrelishvili and Joseph-Belchinski, continuing to advance. When you go, it is a similar point. You need going to the convex fold of the symmetric union of your F. At some point, any times you have the same question.
So the construction is the same.
What?
The construction is the same.
Yes, right. So what is interesting here? The construction is word by word the same. We have some kind of DNA, some similarity. We have some algorithm to produce the corresponding Banach space. But you need different tools. You need different justification. So, turning to this case here. So, if here we use the Crane-Schmuller theorem in order to understand this, here we do not lose our weak compactness. The same is remains true for fragmentability. So, here we need range Julian. And here, for this, in order to see that this one, again, will be good in this sense, to check that the fragmentability is preserved. Again, to check that this will be, again, fragmented on this part. In fact, we have one more difficulty here. So let me explain. In fact, at the starting point, we have here not B star immediately, but in our buzzer date we have X. We start, remember, something like this, right? So we start from F. We need to use, but it's a prototype. It's a final answer. But at the first stage, we start from this point. And at this point, we have two kinds of results. First, that if your family is good on it, your family remains good also on this star. But you need your starting point. Starting point is it visible here? That's both. Starting point is Fx into R, right? And F is fragmented. Now we have two kinds of difficulties. First, by our algorithm, let me say so, in Megrelishvili and Joseph, starting our constructions. The first step is considering C of x. It's not our destination, it is just, some intermediate case. If you take C of x as A, as I already mentioned, this way we went in our proof, then you get at some point immediately f is will be the same, okay, by our condition. F is just part of C of x. So we have f part of C of x, and we have here C of x star. And also here we have embedded, Gerson embedded. Okay? But what kind of difficulties? Now we replace it by its part, B and B star. So B and B star, or if F is not, you can normalize it or take something bigger. It does not matter. Just so at this moment, you need to understand that if you consider something like this, I mean induced pairing from here, it is absolutely canonical. Right? This one is again fragmentable, and it's one of the points that you need to work. The second point I already mentioned, but what happens here, the proofs are not easy, but I avoid it because it's too long. However, I put all the explanations in my file, and if anybody wants, of course, if you have some more questions, I can explain. But that's the two central points, not one, it's two central points. One here. The second step. Now you go to W. What is W? F symmetric union and convex form. And now you need more. Now you need more that this kind of larger pairing remains fragmentability, or the next step, in the similar way, eventual fragmentability. Okay? There's two cases when you need to know a couple of tricks and properties, but it is absolutely not trivial, and even it's quite difficult to find. And what happens for Rosenthal? This explanation is very close. The case of Rosenthal is much more complicated, but we found some way to avoid some other difficulties, and in order to keep the similarity, and one of the inventors was eventual fragmentability. And whenever you can do something for fragmentability, eventual fragmentability, what was eventual fragmentability? For any countable family, you can subtract countable infinite subfamily, which is fragmentable. So it is more complicated, but in a similar way, you can show that these two steps succeeds with these two steps. Okay? In order to continue with the distribution service.
And do you have somehow optimal results that this F has to?
Yeah.
Are your results optimal in the way that F has to satisfy certain property and it's the optimal property, or
optimal?
Yes.
No, I don't. I am not sure that I can give you something, some concrete answer.
Mm-hmm. I mean optimal in this way that using this construction,
yes,
you need exactly this property, and if and it is if and only if. Or is it in this way or not?
I don't understand.
In order to get Asplund space using pure construction,
yes,
you exactly need the property to be fragmentable, or is it possible to find another property which would work as well?
Yes. The proof looks like something very natural. Mm-hmm. But starting from fragmentability and checking these two properties, the proof is not straightforward, but quite natural. But around this circle of ideas, there are still a lot of questions. But I am not sure that I can, maybe I don't understand fully your questions, but at this moment. But maybe we can continue. So this was about, anyway, I planned to explain this part. So now let's go back. So again, now the first case, I mean Rosenthal case, I need to recall something because I said something in abstract way, but let's go and see what exactly we need from Banach space theory in order to succeed and what kind of ideas we use. And I already said that it is absolutely not trivial, and even more, it is very, very complicated, but it is, you can say that it is not so long, but up to some classical results. What kind of classical results we need? So again, what was Rosenthal Banach space? Just space which doesn't contain copy of L1. And there are many good reasons to believe that this class is very important. What are the some very small number of reformulations, equivalent conditions of Rosenthal Banach spaces? Which one is quite non-trivial, a very big result. For example, sub and sub can be reformulated Rosenthal this way, is that if you take any element from the second dual, is a fragmented map if you restrict it on weak star compact ball. Or equivalently, you can write in this way.